Hello, Physics 30s. In today's lesson, we are going to talk about different types of spherical mirrors and then describe how these mirrors can be used to form certain types of images. Learning outcome for today is to describe qualitatively simple optical systems consisting of only one component for both lenses and curved mirrors. For the time being, we're just going to focus on curved mirrors. Later on in the unit of study, after we talk about refraction, then we'll get into the optics of lenses. Okay, so curved mirror, if you want to try to envision what this looks like, let's say you take a spherical object that is hollow. So one spherical object that's hollow that comes to mind for me is a tennis ball. And let's say that you make a vertical cut. So you cut this thing directly in half. And then you're left with just half the sphere. Or I think it might be called a hemisphere. I'm not totally sure about that. All right, now, let's say that whatever material makes up a mirror, that glass or whatever it is, you line it along the inside of the tennis ball. So I have this mirror material that just lines the inside. So this blue curve is what I'm representing on the larger diagram on the screen. That's my spherical mirror. What we're going to do is we're going to go through the terminology, looking at the different parts of a spherical mirror. Then we'll talk about the different types of spherical mirrors, and then we'll get into how we can predict what kind of images form using these mirrors. First piece of terminology is the center of curvature of the spherical mirror. And the center of curvature of the spherical mirror, which we'll represent with the letter capital C, is just the direct center of the sphere. The vertex, which we'll use a capital V to represent, is what we call the geometric center of the curved mirror surface. The geometric center just means, well, if we actually look at the curved mirror surface, so the actual curved mirror surface would be represented by this blue curve. And if we looked at the center of that would be the geometric center, and that would be the vertex. I suppose another way to think about this is if you envision a parabola. If you have like a parabola that goes up and then comes back down, this very top point up here is your vertex. Three, we have the principal axis. If you take a line from the vertex and extend it to the center of curvature and keep going outward, that is what we call the principal axis. It's an imaginary line that extends outwards from the vertex to the center of curvature. And really all it is it's a line of symmetry. It's a horizontal line of symmetry in the way that I've drawn the mirror in this situation. 4, we have the focal point. Now, for the time being, I'm just going to describe where it is, and then we'll get into the significance of the focal point. We describe the convex and concave mirrors in a moment. A focal point is located halfway between the vertex and the center of curvature. So it's the midpoint of the center of curvature and the vertex. 5, the normal line. So it turns out that spherical mirrors also obey the law of reflection. And what the law of reflection tells me is that the angle of incidence relative to a normal line is equal to the angle of reflection relative to a normal line. However, when you look at a curved mirror, it's not very clear where to draw the normal line. Well, let's start off by looking at a ray of light that approaches this mirror. So this ray of light is, in this situation, parallel to the principal axis, and it's directed towards the right. And it makes contact with the mirror at this point. Now, the problem with applying the law of reflection is that when the ray of light hits the mirror is not flat. And the way that we looked at the law of reflection before is we drew a normal line that was perpendicular to the reflecting surface. So for example, if we had like a reflecting surface like this, and then we had a ray of light that's incident upon it, your normal line was perpendicular to your reflecting surface at the point of contact of the ray. But I got a problem here in that I have a curved surface. So I guess the question would be, is there anything we could do to model a flat surface at this point here? And the answer to that is, well, we could do a tangent line. We could draw a tangent line to represent the slope at that point. This is really, really hard to draw, but I'll attempt to draw a tangent line here. So again, a tangent line just represents the slope. That was a complete fail. Let's try that again. So the tangent should be equal on both sides in terms of an angle. This is almost impossible to do with a drawing tablet. Okay, I think you get the point. I'm using a tangent at that point to represent a flat surface. And what a normal line needs to be in is a normal line needs to be perpendicular to that. Okay, so there's my incident ray of light. And it turns out that your normal line is always going to be represented by the radius of the sphere. So if we draw the normal line, it would be represented by this red line. Okay, this is making me feel a little bit better about my horrible tangent line, because it kind of looks like the tangent line is perpendicular to the normal line. So you know what? I did a pretty good job. I should pat myself on the back for that. Yeah, so no matter what, even if like the ray of light contacted here and you drew a tangent, the normal line would still be represented by the radius of the circle. There's an actual mathematical rule for this. There's 2 units of studies in math that I completely despise. One unit of study is in Math 30, dealing with permutations and combinations, and the other one is circle geometry. I've always hated those 2 units of study. There's some kind of like mathematical rule in circle geometry that tells you something along the lines that the radius of a circle and a line tangent to a point are always perpendicular to each other. So you can see this right here. The radius of the circle and the tangent, they do make a 90-degree angle. I'm not quite wording the rule properly, but it's something along those lines related to circle geometry. Now, once we have the normal line, well, then we can measure the angle of incidence, which would be theta 1. Again, the theta 1 is always measured with respect to the normal line. And the law of reflection tells me the angle of incidence theta 1 is equal to the angle of reflection theta 2. And then we can draw the refracting ray. It just so happens here that the reflecting ray bounces back through the focal point, but we'll talk more about that when we get into some of the rules that are going to be used to predict where an image is formed. Before we go any further in talking about the different types of mirrors, we need to distinguish between different types of images. There's real images and there are virtual images. A virtual image is an image which appears to exist inside of the mirror. Let me use an example of this. So the picture I have here is of the side mirror on a car, and inside of the mirror, it appears like I have some trees, and I think there might be like a small picture of a motorcycle. When I look at that mirror, it looks like there's like some other kind of realm inside of the mirror. Like the tree, the motorcycle, the road, they exist, quote unquote, inside of the mirror. And that's how we describe what a virtual image is. A virtual image is basically an image that we can see that only appears inside of a mirror. We call it virtual because we can't actually step into the mirror and go to that tree. Not in the sense of like approaching it in the mirror. Obviously, in the real world, we can approach that tree, but we can't step into the mirror to do it. A real image, this one's a little more complicated to explain. Real images are formed as a result of light hitting a mirror and reflecting, and then being projected onto a screen outside of the mirror. Here's an example of this. We don't really use these anymore. I think I might use an overhead projector once in my classes all year, but these used to be, overheads used to be used pretty commonly to like display notes and whatnot. Okay, now, the way this works is on the overhead projector, and I'll kind of draw it about somewhere like right here, there is a mirror, okay? I don't think it's a curved mirror. I think it's maybe just like a plain mirror, but nonetheless, there is a mirror. What happens is you put an overhead transparency on top of the overhead projector, and there's a light source somewhere in here, like there's a bulb. And what this light does is the light passes through like your overhead transparency and then hits this mirror, and then you can project it onto the whiteboard or onto a screen. Now I can see a bunch of text from my overhead transparency. So what I did is I used a mirror to project an image on an actual object, like an actual real object, which is this screen here. The reason we call it a real image is because we're projecting on the image onto an object that is outside of the mirror. The mirror is here. We're not looking into the mirror to look at this image. This mirror is simply being used indirectly to take light, reflect off the mirror, and then project an image. If I can project an image on a screen, which is outside of the mirror, then we call that a real image. There are two types of spherical mirrors. One is a concave or a converging mirror. I believe concave is the word that's used to describe this mirror more commonly. So the mirror we've been looking at so far, that would be an example of a concave mirror. And there's essentially two defining features to this. First one is the light rays strike the inner surface of the sphere. So I kind of already explained that. I said, like, if you took a tennis ball and you cut it in half and then you lined the inside of the tennis ball with the material that actually makes up a mirror, and if we have a ray of light that approaches and hits the inside of the tennis ball where there's that material, that's a concave mirror. If you take some calculus, I think you talk about the difference between concave and convex in a little bit more detail. Another thing you can look at is you can, if you want to memorize this, is you can think like this ray of light is like going inside of the tennis ball, or like you could think of it like going inside of a cave, hence concave. Take it or leave it. I don't know if you like that as a memorization tool to distinguish. Okay, so that's the first defining feature. You have a ray of light that hits the inside of the sphere. The second one is that what happens when the ray of light hits the mirror, it reflects off of it, and reflects off of it through what we call a real focal point. Now, I just want to distinguish between the real and the virtual side. Okay, so we have my mirror here. The opposite side of the mirror is what we call the virtual side. Presumably I start on this side of the mirror, and then I can't walk across this boundary from like the real world to like the other side of the mirror. So we call this the virtual side. This is what I would call the real side. The real side would be the same side that whatever your ray of light is originating. So this ray of light comes in, and then it reflects off of the mirror, and it is going to reflect off through a real focal point. Well, one of these rays of light is going to do it anyways. We'll talk more about the rules in a second. The rays of light don't always have to reflect through the real focal point, but in one scenario, you will have a ray of light reflect off of the mirror through a real focal point. Second type of mirror is called a convex or a diverging mirror. Basically what we do now is we just flip it around. So if I go back to like my tennis ball, where I cut it in half, instead of lining the interior of the mirror, now you're going to line the exterior. So we flip it around. Convex mirror, also called a diverging mirror. So once again, there's two characteristics of a convex mirror. The first one is that the light rays strike the outside, not the inside of the mirror. And I can see that in this image. I'm striking the outside of the sphere. The second component is that your reflected ray of light, here's where things get a little bit different. If you flip the mirror around, the center of curvature is now on what I call the virtual side. So the virtual side is on the side opposite of the mirror. The real side is on the side where my ray of light is going to originate. What happens here is the instant ray of light hits the mirror and it reflects as if it's coming from a virtual focal point. So if my center of curvature is virtual, it's on the virtual side of the mirror, and the focal point is just half the distance between the vertex and the center of curvature, then I have rays of light reflecting as if they come from this focal point. The reason we use a dashed line here is because the ray of light, like you can't draw a solid line. If I drew a solid line, that would mean the ray of light is actually coming from that focal point, but it can't do that. Okay, it hits the mirror and it reflects as if it's originating from that point. Because when the ray of light hits the mirror, it has to reflect. It can't just like hit the mirror and then suddenly just originate from the focal point. It just reflects as if it comes from that focal point. Now, these mirrors can be used to form different types of images. We've already talked about the different types of images. We can form real images or virtual images. Again, virtual images are images that we see inside of the mirror. Real images are ones that we use real images are ones that can be projected onto a screen by using the mirror. So they can be projected on a screen which exists outside of the mirror. These mirrors can produce images that have a specific orientation and a specific size to them. We'll talk about the orientation right now, and then the example problem will describe the size. If you have an image, like for example, if you looked in a mirror and you saw the image and it's upright, we can refer to that as being an erect image. If we had an image that was upside down, we call that an inverted image. What we want to do is using these mirrors, we want to take these rules, take the rays, and using the law of reflection, I want to use the rays to help predict what type of an image I'm going to get, real or virtual, what orientation I'm going to get, which will be erect or inverted, and what happens to the size of my image. Does my image get larger in size or does it get smaller in size? These three rules we can use to do this pretty quickly. Okay, so let's go through them. Rule 1 tells me an instant ray parallel to the principal axis will reflect through or away from the focal point. Okay, let's look at a picture to show this. In this situation, you have a concave mirror. Concave because you're striking the inside of the sphere. In this picture, I have a ray that is parallel to the principal axis. So I can use this symbol to represent parallel to the principal axis. If you have a ray of light that approaches the mirror parallel to the principal axis, it will always reflect through the real focal point. Now, you might say to me, well, how do you know that? Well, here's what you would have to do to prove this. And this is what we're not going to do because this would involve too much error and this would take way too much time. If you wanted to prove this, what you would have to do is, first of all, at the point of contact, you'd have to draw a tangent line. Again, not very well drawn. And then you'd have to apply the law. You'd have to draw a normal line then. So your normal line would be something like that. It has to go to the center of curvature. So you have to draw a tangent, draw a normal line, measure the angle of incidence, theta 1. I'm going to erase that because I don't like what it looks like. Okay, measure the angle of incidence, theta 1. And then you would need to apply the law of reflection, which is theta 2. Then you could draw your reflected ray, and then indeed you would notice that it goes through the real focal point. We're not going to do this because drawing tangent lines involves quite a bit of error. So we're simply just going to memorize the rule and just use it. So just kind of take this as being true. If you did want to prove these rules, you could do it by drawing a tangent, applying the law of reflection, but we're not going to do that because it's too time consuming and there's too much error involved in drawing the tangent. Okay, so that's the first one. If we have a concave mirror, if a ray approaches parallel to the principal axis, it'll reflect through the real focal point. If we have a convex mirror means we approach, we hit the mirror from the outside of the sphere. A ray of light that's parallel to the principal axis will reflect back when it hits the mirror. Again, the instant it hits the mirror, it has to reflect, but it reflects back as if it comes from this imaginary focal point, which we'll call the virtual focal point. So a little bit different depending on whether we're looking at a concave or a convex mirror. Rule 2. It's kind of like the reverse of Rule 1. Rule 1 is about if you start parallel, you go back through the focal point. Now, Rule 2 is about, well, what happens if you go through the focal point first? An incident ray that passes through or is headed for the focal point will reflect parallel to the principal axis. So let's start off with the case of a concave mirror. So in this case, I have a ray of light from some light source. It goes through the focal point at first, and then when it's the mirror, it reflects parallel. So like I said, it's just the reverse of Rule 1. Rule 1 was parallel back through focal point. Rule 2 is through the real focal point. We just reflect parallel. Convex mirror, a little bit more complicated because your focal point and your center of curvature are now virtual. If you have a ray of light that is headed for the virtual focal point, again, it can't actually get to the virtual focal point because as soon as it hits the mirror at this location, it's going to reflect and bounce back. The ray of light can't hit the mirror and then pass through it to get there. It just targets it. So a ray of light that targets the virtual focal point, when it hits the mirror, it will then reflect parallel to the principal axis. And then finally, we have Rule 3. An instant ray that passes through or is headed for the center of curvature will reflect back through or away from the center of curvature. This is the first rule I would always start with when I draw the ray diagrams, which we'll get into in the examples in a moment. Okay, so in this case, you have a ray of light that passes through the center of curvature. And what happens, the real center of curvature, I should point out, when it hits the mirror, it just bounces back along the same line. This one we can actually quickly justify. So again, think about this. If like we have this point of contact and I want to represent a flat surface, just draw a tangent line at this point. Which is, again, impossible for me to do well. Okay, so that's my tangent line. Now, the reason in this case that when a ray of light that approaches through the center of curvature bounces back along the same line is you have to remember the normal line is the radius. Okay, so I can draw my normal line all the way from this point of contact to the center of curvature. The normal line is the radius. So what's happening here? Well, my instant ray is approaching along the normal line. If I approach along the normal line, that means that theta is equal to 0 degrees. There is no angle between the instant ray of light and the normal line. And if the angle of instance is 0, then the angle of reflection is also 0 degrees, which means you just bounce back along the exact same line. And again, that's the case for a concave mirror. So if you pass through the real center of curvature on a concave mirror, you just bounce back along the same line. For a convex mirror, well, once again, you can't actually get to the virtual center of curvature because it's on the other side of the mirror, but you can still target it. So if I have a ray of light that targets that center of curvature, and again, we can show the targeting just by representing it with a dashed line, and then it hits the mirror, and then it bounces back along the same line at the point of contact of the mirror. Okay, so the thing we're most interested in doing today is we want to, based on the type of mirror, we want to try to predict what kind of image is going to be formed. So I have a couple of examples where I want to, using these 3 ray rules, I want to sketch and describe the image for each of the following diagrams, and then I describe the image by talking about what's the type of image, what's the orientation, and what's the size compared to the object. Okay, so just realized I have a bit of a typo here. Size in comparison to object is, all right, this arrow is a light source of some kind. Now, as we know from light sources, we're going to emit light in every possible direction. So I could have a ray of light being emitted in this direction, a ray of light emitted in this direction, a ray of light emitted in this direction. I'm just going to draw the rays of light being emitted from the tip of the object, and we use an arrow to represent that. It's kind of like just like the maximum point if we look at the actual tip. So it'll be helpful in drawing the image. Now, this object emits light in every direction. But I'm only interested in 3 rays of light that are actually emitted from the tip of the object. And those 3 rays of light are going to correspond to the ray rules we already went through. Okay, so what I want to do is starting from the tip of the object, I want to apply those 3 ray rules. The first one I would always do is the one through the center of curvature, because that's the one that's going to involve the least amount of error. If you take a ruler and there really shouldn't be any error in drawing this one. So what that one tells you is, first of all, we're on a concave mirror. It tells you that a ray of light that passes through the real center of curvature just reflects back along the same line. So if we draw this, we'd have a ray of light that passes through the real center of curvature, hits the mirror. When it hits the mirror, it just bounces back along the same line. So that's applying rule number 3. Now let's apply rule number 1 starting from the tip of that object. And again, this arrow is just what we call the object. It could be a candle, for example. Okay, so that rule tells me on a concave mirror, if I have a ray of light approach parallel to the principal axis, what happens to it? It reflects through the real focal point. So that's how I'd illustrate this. Make sure when you draw your rays, you do have arrows telling you which direction the light is going. Now you'll notice that on the diagram, for my reflected rays, I have this intersection point between the rays. And the intersection point I've represented with this green dot. So this ray goes parallel through the focal point. This one goes through the center of curvature back along the same line. My reflected rays would intersect at this green dot. Now, this intersection point can tell us how to draw the image. And the way we draw the image is, what we do is, at the point of intersection, I would go to the principal axis, okay, straight upward or downward, depending on where you are. And what I want to do is I want to draw an arrow that points from the principal axis to my intersection point. So that's going to be an arrow that points down like this. I'll represent it with a different shape on the screen. So that would look like an arrow that just points straight downward. That's my image. And that is going to be enough to give me information regarding the type of image, the orientation, and its size in comparison to the object. Now, I could do that right now, but I haven't used my third rule, or well, the second rule, but I haven't used the third of the three rule, the second of the three rules. I can actually use the third ray to confirm that I did this correctly in most situations. In some situations, you just cannot draw the rays, but we can use this as like a confirmation. So rule number 2 tells me if a ray of light passes through the real focal point, what it'll do is it'll reflect parallel to the principal axis. And if you look at this, the reflected ray to the principal axis does pass through that point of intersection. So it's a way of kind of double checking to make sure you did this correctly. In this situation, we can do this. We can draw all three rays. Like I said, in some scenarios, you're not going to be able to do it, but I'm going to leave that for the assignment for you to figure out. Okay, let's look at this this image now. So we got this really tiny image that just points straight down. Okay, first things first. What is the type of the image? Well, the image type can either be real or it can be virtual. Virtual means that it would exist within the realm of the mirror. Well, that's on the side opposite from where the rays of light start. This is the real side of the mirror. Okay? The real side is where objects actually exist. So my object, like my candle, does exist here. Okay? And then I have my image forming on that same side. So therefore we call that a real image. The orientation of the object, well, look what it's doing. It's pointing downward, which means the object's pointing upward. If the image is downward, it means it's upside down. An upside down orientation is what we call inverted. Now, what's happened to the size of the image compared to the object? Well, it's quite a bit smaller. So what we'd say is that the image is reduced in size. If, for example, you took a screen, like this could be like a screen, and you put it right here. So again, real images we can form on real objects like screens. If I put a screen here, I would get a very nicely focused arrow that's upside down. Okay, if I put the screen here. If, for example, you had the screen further away, like at this location, what you'd get is you'd see some of the image pointing down, except it'd be really, really fuzzy. It'd be out of focus. So this intersection point we're looking at here is basically telling us where we could put a screen so that the image would be in perfect focus. Okay, let's look at B. Now, this one I have a convex mirror. Convex mirror means rays of light are going to approach and hit the outside of the sphere. Okay, so once again, here's my object, this upright arrow, and we're always going to start our rays drawing from the tip of the arrow. Tip of the arrow being kind of like the maximum height position, which will allow me to get the maximum height position for the image. Okay, let's draw the easiest ray first. So that's the one, that's rule number 3. If you approach again, you're approaching the virtual side. If you approach the virtual center of curvature, and we're targeting it, and we want to show this with these dashed lines, then when it hits this mirror, it's going to reflect back along the same line. Okay, so I can represent that with a lighter blue ray. That's the first rule. Second one, which I'll apply rule number 1. If I have a ray of light that approaches parallel to the principal axis, again approaching parallel to the principal axis, with a convex mirror, it's going to reflect at this position as if it was originating from the virtual focal point. So it bounces back as if it's coming from that virtual focal point. And again, we draw these dashed lines on the virtual side because the rays of light can't actually be in this region. They can just either target the center curvature, or that they can they can emerge as if they're coming from it. Now, if you look at the diagram, what I want to look at is the location of the image is going to be where you have reflected rays intersect. So that's going to be this intersection point, which again, I'll represent with the green dot. The way to draw the image is look at your intersection point, go to the principal axis either directly below or above the dot, and draw an arrow from the principal axis to the dot. So that arrow would this time around be pointing upward. Now let's see if we can get the third rule, the third ray rule, which is again the second one, to actually double check and make sure we did this correctly. So rule number 2 tells me if you head for the virtual focal point, the reflected ray is going to bounce back parallel to the principal axis. Now, for a moment, it seems like, okay, I don't seem to have the correct intersection point, because if I look at this purple line seems to hit down here. Okay, that doesn't seem to be the correct intersection point. Well, here's the thing. When you're trying to figure out where the image is located, you're not using the incident ray to figure out where the image is located. You're using the reflected ray. Now, my reflected ray in this situation is this ray that's going towards the left. At first glance, it seems like there's nothing about this ray that can actually pass through that green dot. But what you can do is you can kind of like backwards extend, or you can take your ray and pull it behind the mirror. And if I take that reflected ray and pull it behind the mirror, then it does intersect at the location of that green dot. So this is a little bit of a weird thing with the convex mirrors. And this is what I would always do. If you don't notice an intersection point, I would take a reflected ray and then just pull it back, and then see if it actually does intersect any of the other lines. And it most likely will, okay? So don't make the assumption that just because you don't see an intersection point at first, there isn't one. Take a reflected ray and then backwards extend it through the virtual side of the mirror and see if you can get that point. Okay, so what kind of image do we have here now? Well, the image is on the virtual side of the mirror. Again, the real side of the mirror is the side where your light rays originate and where you have your object. The virtual side is a side opposite to that. So the type of the image is virtual. The orientation, well, this time around, the arrow's pointing up initially for the object. The image orientation is also pointing up. It's upright or it's erect. How does the size compare to the image compared to that of the object? Well, once again, it's quite a bit smaller. It's reduced in size. I can give one example of this. You may have gone into a grocery store or a convenience store and you've noticed these mirrors that are kind of up in the corner. Well, those are a convex mirror. Again, convex mirror means that it'd be facing with the outside of the mirror towards you. Now, what do convex mirrors do? Well, first of all, convex mirrors give you virtual images. So if you look at the mirror, everything inside the store just seems to exist within the realm of the mirror, okay? Everything I see right there is within or inside of the mirror, okay? So my images are all virtual. They're also erect because when you look at the images of the people here, they're standing upright. The size of the people, though, is quite a bit smaller. It's been reduced in size. The point of these mirrors is what they do is, and this is why they're used as used for surveillance inside stores, is they make all the image objects look smaller, but they increase the field of view. So you can actually see a lot more of the store by making every one of the objects in terms of their images much smaller in size. So that's a good example of a convex mirror. Same thing with the side mirror on your car. The side mirror on your car just makes all the images smaller and increases the field of view. Same thing with the rear view mirror on your car as well. All right, so that's the end of the lesson. And what you can do is complete a handed assignment called Spherical Mirrors. In order to do this, I've provided a couple of hints. I'll just briefly talk about hint number 1. So what hint number 1 I've said is that treat the objects like they are opaque. So here's what I mean by this. An opaque object is something that light cannot pass through. So when you're drawing your ray diagrams, let's say, for example, that you had a ray of light that hit a mirror and it came back like this. If the object is opaque, then that ray stops right there. Okay, you don't draw it going any further back. If it wasn't opaque, then you would draw the ray going through. But the assumption we're making is these objects are opaque, so light cannot pass through them. Same thing, like what we cannot do is you can't take a ray of light and draw it straight. Like we can draw rays of light coming from starting in any direction from the tip, but we don't want to draw a ray of light going through. Okay, that's what we do not want to do because the object is opaque. So I'll say no, do not do that. Point number 2 is it just shows you how to draw some rays when they're located at some really odd positions. Like as you start to get your object closer and closer to the vertex of the mirror, some stranger things start to happen, and it becomes a little more complicated to draw the rays of light. So I kind of just showed you a couple of examples of what this would look like if you're within the center of curvature, or more specifically within the focal point of the mirror. All right, so that's a qualitative description of curved mirrors or spherical mirrors. And the next lesson, we'll get into the math behind it. And I will talk to you.